Okay, but today we talk about federated learning design principle. By the way, can you see my slide? Yes. So what are the three main components of machine learning? Data model loss. What did we talk about last time? Last time we talked about data and models, in particular network data and network models. And today we will combine them. We will combine them by using a loss function and using, and this loss function will also include a regularization term. As I told you in a previous lecture, regularization techniques can also be implemented using modifications of the loss function. And we will use one such modification of the loss functions to implement regularization over networks. So again, network data might arise, for example, in meteorology, where each Finnish meteorological institute weather station generates a local data set. We represent such network data as an undirected empirical graph. So the nodes in this graph, they hold data sets, and the edges between two nodes, they indicate statistical similarities. In particular, they represent or they indicate that the parameters of the probability distributions behind the local data sets are somewhat close to each other. And we also use an edge weight. So there's also an edge weight that quantifies the statistical similarity. Okay, so what do we do then with these networked data sets? Well, we define networked models. We define network models by attaching to each node also a model, and this model could be a scikit-learn model. So here we could define for this node I, we could define a scikit-learn model linear regression. For this node J, we could use the scikit-learn model random forests. Basically, in principle, we can use different models at different nodes. But for the time being, we focus on local models that are parameterized by a parameter vector. So this might be a vector in a Euclidean space with dimension d. So which parametric models do you know about? Do you know examples for parametric models? A Gaussian model. Yeah, Gaussian distribution is a probabilistic model. So in this course, we use the term model to refer to a set of hypothesis maps. So which set of hypothesis maps, which model do you know where each hypothesis map is characterized by a parameter vector? In linear regression, which uses the linear model. So the linear model consists of all hypothesis maps that are characterized by a weight vector, and the map itself is defined by h of x. So we read in the features of a data point and output the prediction for the label, which is W transposed times x. And yeah, so each hypothesis, each such linear hypothesis is fully characterized by the weight vector W. Yes, and we assume that each local model can be parameterized by a weight vector of the same dimension. So this is a bit of restriction, but the ideas and techniques that we develop for parametric models, they turn out to be rather straightforward, can be straightforward, generalized to, in a straightforward fashion, be generalized to non-parametric models. Yeah, what would be a non-parametric model, by the way? Do you know an example for a non-parametric model? A decision tree, exactly. Decision tree is typically not cannot be easily represented by a fixed number of weights because the decision tree might grow depending on the amount of training data we use. Okay, so we then need some assumptions on the data set, on the structure of the data set, similar to this IID assumption. Without any such assumption, there's not much we can do because then we can never look beyond the training set. So, and in federated learning, we sometimes use this clustering assumption, which means that the local data sets form clusters. For example, when these local data sets are weather measurements measured at the Finnish Meteorological Institute stations, then you could say that nearby stations, the weather measured at nearby stations has similar distributions. And in kind of the extreme case would be some of these stations, they measure data which have exactly the same distribution. So the data sets that belong to the same cluster, they can be again approximated as using the IID assumption. So this then brings us back to the basic setup of machine learning. We have data sets. In this case, then this data points are distributed over local data sets, over a network of local data sets. But overall, each data point is drawn from the same distribution. But what sets federated learning apart from basic machine learning is that there are different clusters. So this IID assumption does not hold globally, does not hold for all local data sets, but only holds for subsets or clusters of data sets. So within this subset, for example, these red nodes, we can think about the local data sets in the red nodes of following an IID assumption. But those in the green nodes, they also follow an IID assumption, but they have a different distribution compared to the data sets in the red nodes. And we hope that this cluster structure is reflected by the edges. So we somehow must construct the edges of the empirical graph such that they connect local data sets with similar distributions. So how, I mean, as I mentioned in the previous lecture, this edge set is essentially a design choice, but there are good design choices and there are poor design choices. So a good design choice for these edges is if they connect local data sets with similar statistical properties. Do you have an idea how we could measure these statistical similarities between local data sets? So I would have here in this node, I would have a local data set, a separate local data set. And in this node, I would have another local data set, which might be characterized by two numeric features, each data point. How can you measure if they are similar, these two data sets? The distance between the data sets, yes. So you could determine for each data set a mean or a center and then measure the distance between the centers. Or you use measures of distance between distributions. So you estimate a probability distribution for this data set and you estimate a probability distribution for that data set. And then you compute something like the Kullback-Leibler divergence, which is a distance measure to compare different distributions or the similarity of distributions. Yes, so there are well-known and established methods to come up with a good guess for these edges to represent statistical similarities. But we now, so we assume that we have obtained such a good guess for this edges. So they connect statistically similar data sets. Not always, but most of the time. And I now discuss a method, or what I call a design principle, that is able then to find or to pool the local data sets that can be approximately considered as containing IID data. So these methods that we will now talk about in the next lectures, they can be interpreted as clustering methods. So they cluster the local data sets such that each cluster contains statistically similar data sets. And this clustering is guided by two components, or by two aspects. First, the distributions of the local data sets within the same cluster must not be too different. And second, I must be able to fit well the local data sets. So to find local model parameters that fit well all the local data sets in the same cluster. So it's a form of data-driven clustering. It's not like you could say, I have now this empirical graph, so I have a graph structure, so why not using a graph clustering method? Did any one of you already work with graph clustering or apply graph clustering methods? So there are quite popular graph clustering methods. They are established and a mature technology, I would say, almost like k-means clustering. You can look them up in scikit-learn in the clustering package. But the thing is, the methods that we will develop here, they're not only using the network structure to cluster data points, but they use the interplay between the statistical properties of the local data sets, or you could say the information geometry of the local data sets, and the geometry of the graph. So they couple these two geometries to find the correct clusters of data sets. And how do we do it? Well, the idea is as follows. We try to fit, of course, each local data set. So we have a local data set at each node and a local model. So it seems natural. Let's fit the local model to the local data set by minimizing the average squared error. But we also penalize the variation of the model parameters across edges. So we say, if two nodes are connected, then this means that the statistical properties of the local data sets are similar. And this in turn should mean that we should use similar model parameters. If they have similar statistical properties, then we should use similar model parameters. So we penalize somehow the deviation of the local model parameters at connected nodes. And this penalization needs some measure. We need something that we can use as a loss, like the squared error loss. So we need some function that reads in the difference between those two vectors and gives us a number that increases, for example, with increasing norm. So we could use the norm itself, but we might also use the norm squared. So the principle that we develop now is flexible in the sense that it allows for different choices of this function here. I call this a penalty function, which measures the difference of or variation, you might call it a variation, of the local model parameters across an edge. And now we can also use the edge weights. So we can use this measure of amount of similarity to scale the variation. So we want to penalize the variation across an edge even more if it has a large weight. So if this is large, then this penalty term will be scaled up. Okay, and we sum these variation measures over all edges. So we want in general over the whole network, we want to have similar model parameters at well-connected nodes. So for example, in this toy graph, we would like to have similar model parameters or identical model parameters over these nodes, which are well connected, and over these two nodes, for example. We tolerate, if we need to tolerate a variation, a change of model parameters, then we tolerate it over a few edges with small weight. We could call this boundary edges. Okay. So just to point out a few special cases for the penalty function and which are used in the literature, in federated learning literature. So one special case is the norm itself. So this penalty function then delivers the norm of the difference in the weight vectors. Some methods use the squared error norm, And it's a design choice again. It's like the loss function in basic machine learning. It's a design choice. And there are computational aspects why we want to prefer, for example, this loss, because it's a smooth differentiable function that we can minimize with gradient descent. There might also be statistical aspects that might favor using this non-differentiable function, this norm. So there's a question or comment, which is, let's say all local data sets come from the same distribution, but due to small amount of data, they differ. So clustering will then reinforce these differences, leading to overfitting. Isn't that a problem? Yeah, so this depends. If the data sets, so there are regimes, and that's actually a current field of my research. There are regimes where these local data sets would be much too small to fit the local model. So the local model could have effective dimension 100, and the local data set has only 10 data points. And it turns out that even in such regimes, you can test the similarity, but you get noisy estimates because these are small data sets. Sometimes you will add an edge between data sets that from different distributions, but on average, you will make good connections, and sufficiently many, such that when you minimize the overall total variation term, will couple all the data sets that have the same distribution, even if you have in each local data set only a tiny sample size. So these total variation minimization methods, they are able to pool the data sets, even if they would be, when you look at them individually, much too small and would result in overfitting. However, since you pool them together, so you couple the local model parameters to be identical over all nodes, this is equivalent to pooling the training set. And then when you pool it, it becomes sufficiently large overall to avoid overfitting. Yes. But yeah, the precise conditions on how large the local data sets have to be, this is still research in progress. So we are still working on that. Any other comments or questions? Okay, so now we have this penalty function, which, so if we would minimize, if we only would minimize this total variation or generalized total variation term, then the solutions would be trivial, because if we use and typically we always will use a penalty function that is minimal for zero deviation. So we want ideally, or the minimum penalty we get when the local model parameters are identical. So we can easily minimize this generalized total variation by using a constant weight vectors. And then the total variation would be minimal. So in order to get a meaningful machine learning algorithm, a federated learning algorithm, we also need to take into account, of course, the local data. So we also want the model parameters to yield a hypothesis that predicts well the data points in the local data set. And the quality of this prediction we could measure via mean squared error. So this local loss could be the mean squared error on a local data set. So we predict the labels of all the data points in the local data set at node I. So okay, here I have to now use a different index for the data point in the local data set. So this local loss would be the mean squared error over the local data set. Okay, yeah, but then it seems natural to minimize the sum of both. And here we have now this is our federated learning design principle. This is an instance, by the way, of empirical risk minimization. Empirical risk minimization we have here, or let's say regularized empirical risk. This sum of local loss functions can be interpreted as empirical risks or average empirical risk. And this total variation term here is a regularizer, is a regularization function. And we also include in this design principle a tunable regularization parameter. And the effect of increasing this regularization parameter is to favor solutions which make this total variation term small. And this total variation term is small if the weight vectors are constant over well-connected nodes, which means they should be clustered. Okay. And here, point out the special case that you might have heard. So network lasso is a special case of this design principle, which uses the norm as the penalty function. Another special case is called MOCA. I only know the abbreviation. I didn't find the full name of this method. I only have found the term MOCA. So this is another very popular method. At least the paper who introduced this is very well cited. It's another special case of our design principle, which uses the squared norm as the penalty function. Okay, so now we have our design principle, and not too surprising, the design principle is an optimization problem, as always in machine learning. Most machine learning problems or most machine learning models are optimization models, such as empirical risk minimization. And here another variant of an optimization problem is this generalized total variation minimization. So the two key questions we ask in machine learning are then all, or at least two key questions are the computational properties or computational aspects, how to compute the solutions efficiently. So how do we find good model parameters that minimize this objective function? And the second question is, are the solutions statistically useful? So even if we manage to compute the solutions efficiently, do the solutions provide us with good model parameters? In particular, do they overfit or not? So I will briefly sketch the computational aspects. And we have to consider here federated learning applications that are implemented over networks with unreliable links and unreliable devices. So consider a federated learning application being an app that runs on a smartphone, and you can exchange or the links in the empirical graph are Bluetooth connections between smartphones. So sometimes you might not have a connection. You might not be able to exchange messages between the nodes in the network, and sometimes also the nodes themselves might fail because you're out of battery on your smartphone. So we need optimization algorithms that are robust to such hardware or infrastructure failures or imperfections, in particular robust against stragglers. So we want optimization algorithms that can tolerate that once in a while a few of the nodes will fail to function. But there are also other federated learning settings. So this is just one type of federated learning setup. You might also look at federated learning applications that are implemented with high performance computers or supercomputers. And then you might have different constraints that are related to latencies instead of coping with the stragglers. So this is just to point out the very different settings or application settings where we want to have federated learning algorithms to work well. And depending on this application setting, you might prefer one method over the other. So one method is obtained by considering this total variation minimization for local models being linear regression models. So this gives us this error here, which is the average squared error on the local data set. And as penalty, we use the squared norm, squared Euclidean norm. So this is one instance, one special case of our design principle. And it turns out you can write this optimization problem as a quadratic program. So this here is equivalent to this optimization problem for a suitable choice of Q of the matrix Q and the vector Q. And it turns out that you can choose the matrix Q as positive semi-definite, which is nice because this tells us that this is a convex function. A convex function that is also differentiable. So how could we solve this optimization problem? How can we find the minimum of a differentiable and convex function? Yes, gradient descent. We can do gradient descent. And if you work out the gradient descent, the gradient step looks like this. So it's essentially applying a linear map. So this here is a linear function, a linear map applied to the previous iterate. So this seems nice. What is a bit hidden in this notation here, that this vector or the iterates, they are stacked vectors. So they consist of the weights at the first node until the weight at the last node. So we stack the weight vectors, the local model parameters, over all nodes into a vector. And this matrix here, Q, has a specific structure. In particular, its non-zeros are related to the edges in the empirical graph. So it turns out that this update can be implemented as a message passing rule. So in each update step, you have to pass messages between neighboring nodes. So gradient descent for this federated learning problem can be implemented using message passing, local message passing protocols. Okay. Yeah, by the way, how should we choose the learning rate here? This is an important design parameter. Do you know a choice? Yes, 1/k. 1/k works always. This is the nice thing of this choice 1/k. Because you don't need to know any bounds on the eigenvalues, for example, of this matrix Q. And the eigenvalues of this matrix Q depend on the eigenvalues of the quadratic form of the feature matrix of all the local data sets, and the eigenvalues of the Laplacian matrix of the empirical graph. So this might be non-trivial to bound or control these eigenvalues. So one safer option is to use 1/k as step size or learning rate, to ensure convergence of these iterates to the minimum of the objective function. Okay, that was what I wanted to say about the computational aspect. So if we use linear regression models as the local models, and we use the squared norm as penalty function, then we end up with something that we with a machine learning problem or federated learning problem that we can solve with gradient descent. Okay. Then regarding statistical aspects, how do the solutions of this optimization problem look like? And to say something about the solutions or the structure of the solutions, it's useful to look at the graph Laplacian. So the graph Laplacian is assigned to can be constructed from the weights of the edges. So once you know the edge set and the weights of the empirical graph, you can construct the graph Laplacian. And you can rewrite this regularization term actually as a quadratic form in an extended graph Laplacian. So this here is the Kronecker product. The Kronecker product means you take if this is the graph Laplacian, L11, then taking the Kronecker product means you multiply each entry of this Laplacian matrix with the identity matrix of suitable dimension. So it's an extended or upgraded graph Laplacian matrix that we use here in this quadratic form. And once you write the objective function using the graph Laplacian, you can get some mileage in the analysis of the solutions by taking into account that when lambda becomes large, so for large lambda, you put the focus or you emphasize this second term in the minimization problem. And to make this second term small, based on this identity, means these weight vectors, they should basically be linear combinations of the eigenvectors of this graph Laplacian vector with corresponding to the smallest eigenvalue. And as I briefly sketched last lecture, these eigenvectors are actually the piecewise values, or have piecewise constant values over the clusters in the graph. And the size of the cluster, or the size of the resulting clusters, depends on how much emphasis we put on this regularization term. So the larger the lambda, the larger the clusters of the solutions of this GTV minimization will be. So this green box here, this is the indicates the subset of nodes over which the solutions, over which the learned parameter vectors will be approximately constant. And the larger you make the lambda, the more clustered, or the larger the clusters become over which the solutions, the learned parameter vectors, are constant. So you have two special cases. The one special case is when you choose lambda equal 0. When you choose lambda equals 0, this means no clustering at all. So you have no regularization term. This would mean you train each local model separately, because then this sum decomposes into independent optimization problems for each node. So this could be called personalized federated learning, or it would be then an extreme case of personalized federated learning. And the other extreme case, if you make lambda very large, beyond a certain critical point, it turns out that the solutions for this problem will be approximately constant over all nodes. So this is the pooling where you pool all local data sets in the graph together. And this critical value depends on two things. It depends on the local data sets themselves. So it depends on in this case, on the feature matrix and the label vectors at each local data set. And it depends on the graph structure. So when this phase transition, let's call it phase transition, happens, so the threshold value for lambda, above which the solutions of GTV minimization become constant, this depends on the network structure of the empirical graph and the shape of the local loss functions. And these local loss functions in turn depend on the features and labels of the data points in the local data sets. Okay. How much do I have left? Yeah, let's briefly go over some interpretations. We have around 10 minutes left. Some interpretations. So this learning problem, or the algorithms that we obtain by solving this learning problem, they can be interpreted as multitask learning algorithms, because each local data set and fitting a local model on the local data set is a learning task. So what we now do is we couple these learning tasks, and this is a form of multitask learning. So we're not separately learning the local models. We do not solve the local learning tasks independently, but we couple them by using this total variation as penalty term, or as regularization term. So this GTV minimization methods are an instance or a special case of multitask learning. Another interpretation comes from the fact that the solutions to this learning problem are constant over clusters. So being constant over clusters is equivalent to pooling the local data sets in the same cluster. And this is what locally weighted learning does. So in locally weighted learning, we weight the data sets at neighboring nodes either 1 or 0. So some are completely used or are not used at all. So what we do when we solve this GTV minimization, we do a form of locally weighted learning. And the ranges over which we locally average, this is guided by the empirical graph. So this is not pre-specified, because these clusters, as I mentioned before, the clusters that we obtain from GTV minimization, they depend on the network structure and the local data sets themselves. They interact with each other. Okay, another interpretation is a form of generalized convex clustering. where you have for each node, you have a reference vector, or like a vector AI, and you want to find model parameters that do not deviate too much from this pre-specified vectors, but also have a small variation over the edges in the graph. So this is such problems are known as convex clustering problems. Yeah, I might skip this ones. Yeah, it's a bit maybe too abstract at this point. Yeah, just before I finish this lecture, I want to give a glimpse on how we can extend the concepts developed so far. So far, we used the difference between the model parameters. So we had a local data set at node J, we had a local model parameter at node J, and we had a local data set at node I and a local model parameter at node I. And we then computed the difference between those two and the norm of those. But what if we don't have any model parameters anymore? So we don't have model parameters, for example, if we use decision trees. So we could use a decision tree at node I and a decision tree at node J. So how do we compare decision trees? How do we compare trained decision trees? Well, one way to compare them is by looking at their predictions at the common test set. So we train a model here for node J on the data set for node J, and we train another model on the data set for node I. This can be arbitrary models, non-parametric, parametric, whatever you want. The thing is, we get a hypothesis. A trained model means a learned hypothesis that can be used to predict the labels of data points. And in particular, we use them to predict the labels on these two data points here, which we call a test set, and that is used by both nodes. So this test set is kind of the referee who decides, or let's call it a scale, which compares this learned hypothesis, the blue hypothesis, with the dashed green hypothesis. So, and then we use the difference between the predictions. So if these predictions are real numbers, we can compute the squared error between these predictions. And we have a measure for the variation of non-parametric models. Yeah, so this is just a brief glimpse on how to extend this total variation minimization for non-parametric models. And you can read much more detail about this in the lecture notes in section 7, I think. Okay, so to wrap up, today we have introduced the design principle of training local of federated learning algorithms, and this principle amounts to regularizing the training of local models using different measures of variation. So instead of just training each local model independently on a local data set, so we could train a model here on the blue data set and a model on the green data set. We could do this if the local data sets is sufficiently large. So in some applications, this might be the best way to do. So no need to worry about coupling the training. But in other applications, these local data sets are too small relative to the local models. So we need to somehow couple the training. And one way to couple them is by requiring a small variation across the edges in an empirical graph. Yes, so we therefore use GTV minimization. So we minimize the sum of two components. One component are the prediction errors at the local data sets, because we want the local model to do well on the local data set, of course. But we also want the variation over the edges to be small. And this then results in GTV minimization as a design principle for federated learning algorithms. And what this GTV minimization does, it implicitly pools or clusters the local data sets into clusters within which we can approximate them as IID realizations of the same distribution. Yeah, and as pointed out, the cluster structure of these solutions to GTV minimization, they depend on both, on the edge set of the empirical graph and on the shape of the local loss functions. Okay, that's all from my side. Are there any questions? There's one question. How can we force non-parametric models to be similar? Yes, so we can force non-parametric models to be similar by forcing them to have the same, to deliver the same predictions on a test set. In particular, we can use a test set which is very wide. So we can use as test set, for example, a super large number of data points that cover the whole feature space of both local data sets. So forcing then the left model and the right model, trained model, to have the same predictions on the test set forces them, they can only satisfy this constraint if they are identical. But this is an extreme case. Normally we don't want that. So we want a local model that fits well the local data. So this could be, so okay, let's use the blue one. If we have blue data points, let's use a blue model. Why not? So we could train a local model here that looks like this. Batch fits perfectly the local data set, but it's not useful outside the local data set. So the test set could be is something like a validation set. So we use here we could also learn a green model on this other data set, which also does not do a good job outside the local data set. And we might spot such cases or might avoid such cases by forcing the green and the blue one, to agree on the test set. It might also happen, if we have bad luck, that they agree on the test set, but still are bullshit outside the local data sets. But the hope is, and we could try to choose the test set in a way such that forcing the left and the right model to agree on the test set also prohibits them to go crazy outside the local data sets. Yeah, but the precise conditions, how to choose the test set to achieve this is subject to current research. So in particular, my group is looking at these questions. Any other comments or questions? Another question, can we use data from the connected local data set, but give them smaller weights? I'm not sure what you mean by connected local data set. We have local data sets at each node, and we have a test set that is shared by all nodes, or at least by each pair of nodes. Yeah, so local data sets that are connected in a graph, you mean a local data set here is connected to the local data set here because the nodes are connected. So this per se is not enough. If we would only use this connectivity to say these two should be pooled, then we would always pool all local data sets as soon as we have a connected graph. So we typically need to be more selective for when to pool local data sets. So there should be, let's say, the nodes should be connected by many different routes instead of only one. But what exactly is the sufficient connectivity? Depends on the overall structure of the empirical graph and the local data set. So this is something that is not obvious to find out unless you actually solve GTV minimization and then analyze the solutions or the weight vectors that solve this problem. Yeah, so there's a weight. Yeah, you can also use here how you combine the local squared errors and the errors, the discrepancy errors here on the test set. There you can include a regularization parameter lambda. but how to choose them optimally is non-trivial. So it's a tuning parameter that you might choose by validation techniques. Okay. So yeah, that's it for today. If something else comes up, please do not hesitate to ask questions and comment on Slack or reach out to us by email. Thanks a lot. Have a nice evening.